Hello students, now we are looking at transition elements in class exercise 3. So for the first question, we are told that we have 4 different octahedral complexes, so we need to take note of this term. We are looking at octahedral complexes obtained by reacting aqueous cobalt 3 chloride with ammonia under different condition. If you have heard me during tutorials, you might be aware that aqueous cobalt 3 does not exist. It's hypothetical because cobalt 3 will oxidize water to give oxygen gas. Yep. However, this is an old A-level question, and I do believe that when they set the question, they might overlook this particular fact. Yep. But anyway, as a question itself, it is still okay to do it. Just do take note that cobalt 3 aqueous does not exist in most situations. Okay, so what is stable in aqueous chemistry is cobalt 2. You were told that different proportion of chlorides are being precipitated out when each complex is treated with aqueous silver nitrate. So what this portion of the question is trying to tell you is that you have a large transition metal complex which is positively charged, and then you have some free chloride ions. So only the free chloride ions will be precipitated out by silver nitrate. The chlorides which are acting as ligands towards the cobalt 3 center will not be precipitated out as the silver chloride. Okay, so essentially this is what this particular piece of information is trying to tell you. And when you look at the empirical formula over here, so you have we have altogether 4 compounds. The difficult part of the question, of course, is that they seems to have a similar empirical formula. Okay, so at least for A and B. Yep. Then of course for C and D, you have different ammonia ligands from that of A and B. Okay, so from here, if you look at the second column, you notice that the number of moles of silver chloride precipitated out per mole of complex, it reduces from 3 to 2, and then from 2 to 1, and then from 1 to 1. Yep. The last column is not very important right now, except towards the last part where we need to draw out the structure of the complex. Okay, or rather for part B. Okay, so first of all, if you look at 1A, you are required to consider the number of moles of silver chloride precipitated out, and then determine how many chloride are ligands in each of the complex. Okay, so over here it should be quite straightforward, because for compound A you have 3 chloride being precipitated out. Yep. So therefore the number of chlorides coordinated as a ligand would be 0 for A. So I'll just put here, so it will be 0 for A. Okay, and then for B, because you get 2 moles of silver chloride being precipitated out, so there will be 1 chloride acting as the ligand. Then for C and D, I'm expecting 2 chlorides to be acting as the ligands. Okay, so for part A, in our case here, it will be relatively straightforward, simply by just looking at the number of moles of silver chloride being precipitated out, and some of the ideas which I highlighted to you guys earlier on. Okay, then for part B, suggest a structure for each of the complexes A to D. Okay, so we are simply just looking at the complexes, so there isn't a need for us to include the chloride counter anions. Okay, so we just need to be a little bit careful about what we are drawing. Okay, so for the first compound, or rather for the first complex A, what we have is all the 3 chlorides are not part of the ligands. So what we need to draw here is simply a big square bracket, and then we have a cobalt center. Okay, and then we have dative covalent bonding towards the cobalt center. Okay, remember we need to represent dative covalent bond with arrow. Okay, and then we'll input this as NH3. So remember that the bonding begins by the atom with the lone pairs of electrons. Okay, so do not anyhow draw your nitrogen in. Okay, so remember to put it like this. So H3N and then H3N. So do remember this. Okay, yep. So we don't want sloppy piece of work like this. Okay, so I'm just going to write a sloppy piece of NH3. So it's a negative example, maybe like this, maybe like this. Okay, so this is not accepted. Okay, so what we are accepting is simply like this, NH3. Okay, so you guys have to be a little bit careful when you draw out the structure. Okay, yep. And then next, we are looking at B, where there is one chloride ligand. So does the complex have a significant or has a dipole moment? Obviously, it's yes. Why yes? Well, I mean, the answer is obvious because the molecule or the complex is not likely to be symmetrical. Okay, so for B, I'm just going to draw again the same thing. I'm going to draw in a cobalt right in the middle. Okay, so earlier on I forgot to put a charge. Okay, so please put the charge as 3 plus. Okay, so for B, I'm going to put the charge as 2 plus. Why is that the case? Because one of the ligand is negatively charged. In our case here is chloride, so I'm just going to put chloride here, Cl, and then dative covalent bond to the cobalt 3 center, and then I'm just going to draw the dative covalent bond from the ammonia. Okay, so something like this, NH3 and H3 and H3 and then H3N. Okay, so please develop the good habit. Remember, the origin of the dative covalent bond must come from the lone pair of the atoms. Okay, so in our case here, it will be chloride and nitrogen, or chlorine and nitrogen. Okay, yep. And then for C and D, there are two chloride ligands, but if you have two chloride ligands, the complex can either be symmetrical, okay, or not so symmetrical. So the symmetrical one will not have a dipole moment. So that means that the two chloride ligands are trans to each other, or they are on opposite ends. Okay, so the one that is not so symmetrical will have the chloride 90 degrees to each other. Okay, so with this fact in, I think we can easily draw out the complex. So I'm just going to draw out, okay, this is CO. Okay, and then it will take on a plus charge. Okay, right, and then I'm just going to represent the chloride again with orange. Okay, so remember this is not the symmetrical one, so the two chloride ligands are 90 degrees to each other. Okay, and then for the rest, you're going to have 4 ammonia ligands pointing towards the cobalt center. So remember this, you have to ensure that the ligand, the dative covalent bond must come from the lone pairs of electrons on the relevant atoms. Okay, so next I'm going to just draw out this again with a plus charge and then with a cobalt center. And then in our case here for D, remember earlier on that there's no net dipole, so therefore the two chloride ligands are opposite each other. Okay, so I'm just going to draw this out, NH3 and H3 H3N and then H3N. Okay, so these are the 4 complexes which you're supposed to draw for parts B. Remember that for parts B, you're supposed to suggest a structure for each of the complex A to D. Okay, yeah, so the question asks you for complex, they didn't ask you for compound. Okay, next we'll look at question 2. Okay, so you were told that the use of data booklets is relevant to this question, so just make sure that you have your data booklet with you when you are doing the part which requires you to maybe refer to some of the details. You were told that cobalt is a typical transition element, and then you are given some details, and then you were also told that cobalt forms many colored compounds and complexes. So these are some of the things which if you remember one of the enrichment videos which I did for the aqueous chemistry of cobalt, I have show you some of the very interesting colors which you can get for cobalt. So the few interesting colors are all listed in the flow chart over for this particular question. Yeah, so if you're interested in reviewing that particular videos to look at some of these color, the link is in the description below. Okay, so please go and click on the link to appreciate some of the interesting aqueous chemistry of cobalt. Before we look at the question, you might just want to look at some of the details in the flow chart. Okay, so first of all, we begin with over here the pink solutions. In this case, you expect it to be the aqueous complex of cobalt 2. Yeah, so this is likely to be hexyl aqua cobalt 2 complex. Okay, so hexyl aqua cobalt 2 is CO H2O6 with 6 water ligands, 2 plus. Okay, and then after ammonia is being added, you get the green blue PPT. This shouldn't be very unfamiliar to you, because you know that when you are adding aqueous ammonia, the first reaction that is likely to take place is the acid-base reaction between ammonia and water. Yeah, but because ammonia is a weak base, so it will ionize very slightly in water, and in the process it gives us ammonium, okay, as well as OH minus, and then the little bits of OH minus in our case here will result in the ionic product of cobalt 2 hydroxide to exceed its KSP. Yep, so this will lead to the precipitation of cobalt 2 hydroxide, which is the green blue PPT. Okay, so this particular reaction, it shouldn't be very unfamiliar to you. Essentially, the role of ammonia here is a base, because it is involved in the acid-base reaction with water. Okay, and this is being asked in A1, so in this case, the role of ammonia is the base. Okay, for reaction 2, what exactly is happening here is that I'm adding excess ammonia. So the excess ammonia in our case here, because the bulk of the cobalt 2 has already been precipitated out as cobalt 2 hydroxide, so now the excess ammonia, right, will remain largely as molecular ammonia, which means the unionized species. So it will result in the ligand exchange reaction between hexyl aqua cobalt 2 as well as ammonia. Okay, so the ammonia will replace or displace the water ligands. Okay, and then this will be the balance equation we are looking at. So equilibrate, and in the process it gives us the hexylamine cobalt 2 species with 6 ammonia ligands, okay, as well as kicking out 6 water molecule. Okay, so in this case ammonia acts as the ligand, yeah, because the excess ammonia undergoes ligand exchange with the water ligand in hexyl aqua cobalt 2 complex. Okay, so this is pretty straightforward, and that's why you get a different colored solution. Okay, so initially it's pink, now you're getting a yellow solution. Yeah, so if you remember what I mentioned during tutorials, you will have remembered that color change is either of the two process, that is ligand exchange or redox. Yeah, usually we will test you either one, or it could be sequential. Okay, so for example, in this case, it is sequential, because after ligand exchange, over here on standing in air, yeah, the complex, the hexylamine cobalt 2 complex change in color from yellow to dark brown. Yeah, so this is a clear example of a redox reaction. So it's an oxidation reaction in our case here. Okay, yep, and then what exactly is happening between the pink solution after adding concentrated hydrochloric acid to get a blue solution? So what exactly is happening here is ligand exchange, because the excess chloride ligand will displace the water ligand, and in our case here, it will give us a tetrachlorocobalt 2 complex. Yep, and you might be wondering, why is it that I will need concentrated hydrochloric acid? Why not just normal hydrochloric acid? Yeah, number one is we need a lot of chloride for the displacement to take place, and also chloride is a weaker ligand than water. Yeah, so in our case, where we have a weaker ligand than water, we'll definitely need a lot of it, yeah, for the displacement or for the ligand exchange to take place. Okay, then for A part 2, we are supposed to suggest the formula for compound B. So in our case here, I think we have discussed it. It should be the cobalt 2 hydroxide. Okay, so I'll just write it as cobalt hydroxide, OH2. Yep, and then for part 3, we are asked what is the formula of a complex present in cobalt 2 chloride and the cation present in C. So essentially it's over here. Yeah, so basically we're just copy what we have here. Okay, so we're going to have here is hexyl aqua cobalt 2 complex. Okay, so I'm just going to write this in 2 plus, and then after that for the one in C, that will be the hexyl amine cobalt 2 complex. Okay, like this, right? And then for part 4, we were told that aqueous cobalt chloride does not oxidize on standing in air. Okay, so use relevant E0 value to explain why this is so. Yeah, so you notice that hexyl amine cobalt 2 will be oxidized in air, but not hexyl aqua cobalt 2. Okay, why is that the case? We will need the data booklet to help us. Okay, so first of all, I think we need to go to the relevant information over here. We will need cobalt 3 cobalts. So this is the piece of information we need, cobalt 3 cobalts. Yeah, so the reduction potential is 1.89 volts. So we're going to copy this down. So cobalt 3 plus aqueous plus electrons equilibrate to give us cobalt 2 plus aqueous, and that will be plus 1.89 volts. Okay, and then it does not oxidize on standing in air. Use relevant E0 values. Okay, so over here, what we have is aqueous cobalt 2. So for aqueous cobalt 2, we are probably not expecting the solution to be alkaline, so likely that the solution is acidic in nature, or maybe towards neutral. So when we are choosing our values, we will need to choose the one in acidic medium. So probably this is the one we are going to choose. If you wish to choose the one in alkaline medium, you can do that as well, because the answer will be the same. But remember that when it's in the alkaline medium, cobalt 2 is likely to be cobalt 2 hydroxide rather than hexyl aqua cobalt 2. Yeah, so of course the question here is not very clear. What exactly are they asking? Are they asking about the aqua complex, or are they asking about the cobalt 2 hydroxide? But based on the context, they seems to be asking about the aqua complex. Okay, so we're just going to copy this in. So just going to copy this. So this O2 plus 4H plus 4 electrons, and then equilibrate to give us 2H2O L, and then this is plus 1.23 volts. Okay, so we're going to calculate E cell. So E cell is equals to 1.23 minus 1.89. Okay, so I'm just going to punch the calculator. So we're going to get minus 0.63 volts. Okay, and this is actually less than 0 volts. So therefore the reaction between cobalt 2 and oxygen is not spontaneous in air. Okay, so that's why cobalt 2 does not get oxidized to oxygen when left to stand in air. Yeah, then you might be wondering, what about the hexyl amine cobalt 3 to hexyl amine cobalt 2? Unfortunately, the values is not given in the data booklets. If you search online, you will be able to find the values, and you realize that the reaction is actually spontaneous. Okay, so that should give you a clue that after ligand exchange, the reduction potential value changes as well, and we have talked about this in our earlier either in our lectures earlier on, or in some of the data booklet discussion. Okay, so if you are in doubt, maybe you can go back and review some of those videos. Okay, yeah. Then finally, for part 5, we have cobalt chloride converted into A. So 1 mole of cobalt chloride reacts with 2 moles of HCl, and no other compounds is formed. Okay, so basically this is just asking you for the formula of the complex ions. Yeah, so if you look at the clue given, you should be expecting tetrachloro cobalt 2. Okay, so COCl4, the overall charge is 2 minus. Okay, so this is 2 minus. Okay, yep. And Finally, okay, so there's a additional part. We have a part 6 over here. We were told that dilution of A with water produces the original pink color. So by means of an ionic equation, explain why this is the case. Okay, we have also demonstrated this in our earlier videos on the extra or enrichment chemistry on cobalt, aqueous cobalt chemistry. So if you wish to, you can, as I said earlier on, go and visit the video, which I have already placed the link below. Okay, so what we are going to do here is if we are going to dilute A, so what we have is maybe we should write out an equilibrium reaction between hexyl aqua cobalt 2 as well as tetrachlorocobalt 2. Okay, so we're just going to write this in. So CO H2O6, okay, CO H2O 2 plus aqueous plus 4Cl minus. Okay, and then we're going to equilibrate to give us COCl4 2 minus aqueous plus 6H2O. Okay, so this learning objective is on chemical equilibrium. So we have to be a little bit careful, because the usual misconception is that we say that when we add water, the position of equilibrium will shift to the left so as to remove the additional water being added. Yeah. Why is this a grave misconception? Because water is the concentration of water is a constant in this equilibrium. Yeah. So the main idea is not to talk about water, but it's easier to use the idea of reaction quotient to discuss this particular question. Okay, so I'm just going to use the little bit of empty space here to discuss. Okay, so what we have is we can write out a Kc expression. So the Kc expression for this will be COCl4 2 minus, okay, to the power of 1, and then divide by the hexyl aqua cobalt 2, so CaH2O6, and then this is 2 plus, and then Cl minus to the power of 4. Okay, so if we are going to take out the volume term, so what we're going to end up with is the number of moles of COCl4 2 minus divide by the number of moles of H2O6 2 plus, and the number of moles of Cl minus to the power of 4. Okay, so if you're going to take out the volume term, so this will be multiplied by 1 over V divided by 1 over V to the power of 5. Okay, so if you're going to just cancel, so the V to the power of 5 term will be brought up. Okay, so this whole thing will then I'm just going to erase this. It will then become I just write in red. Okay, it will become V to the power of 4. Okay, oh, there's a shift in sorry, I wonder why is there a shift. Okay, so I'm just going to erase this. Not sure why is there a shift. Okay, so I think there's something wrong with this software already. Okay, so I'm just going to rewrite it so that you guys are not confused. Okay, so for 2 minus divide by the number of moles of H2O6 2 plus Cl minus to the power of 4 multiplied by V to the power of 4. Okay, so if you have V to the power of 4 over here, what happens when you add water? Okay, so when H2O is added, okay, so the volume increases. So when the volume increases, QC will be bigger than KC. Yeah, so when QC is bigger than KC, in order to restore equilibrium, yeah, the number of the numerator, in this case the number of moles of tetrachloro cobalt 2 complex must drop, and the denominator must go up. Am I right to say that? Yep, because it's either the numerator goes down, the denominator goes up, or the numerator goes up, the denominator goes down. Okay, so each of them will have opposite effects on the final QC. Okay, so because QC is bigger than KC, I need to adjust the value of the numerator and denominator in such a way that it has to be reduced back to Kc. Okay, so the only way to do that is to ensure that the denominator goes up, the numerator goes down. So in this case, for this to happen, the POE, the position of equilibrium, will shift to the left. Okay, so remember this, POE will shift left in order to restore the equilibrium. Yeah. So in this case, that's why when we add water, the original pink color was being restored. This is due to the formation of hexyl aqua cobalt 2 complex. Okay, yep. And then finally we have question 3. For question 3, it's quite a difficult question back then. It's only one small part. Okay, so you were told that when copper 2 oxide is stirred with liquid ammonia, so I'm just going to write copper 2 oxide first, stirred with liquid ammonia, it dissolve to give a colored solution. So during this reaction, the oxide act as the Bronsted Lowry base. Okay, so this thing plus ammonia. So remember, you don't anyhow introduce water. Okay, and then they ask you to suggest an equation for this reaction. Okay, so remember this. We are being told that the oxide anions, in our case here, this is the oxide anions, it acts as the base. Okay, so if you act as the base, then what is the acid? The acid can only be ammonia. Okay, so therefore our byproducts, okay, after O2 minus act as the base, can only be OH minus. Am I right to say that? And then in the process, NH2 minus. Okay, and do take note that this is doubly charged because or rather the total charge on the right hand side is -2. Yeah. Are we clear about what exactly is the colored solution? Actually, we are clear what is the colored solution because the copper 2 does not change. So remember that a colored solution involving copper 2 and aqueous ammonia, or rather liquids ammonia, okay, liquid ammonia, there's only one, which is the tetraamine copper 2 complex. Am I right to say that? So this is the complex we are familiar with, and this is 2 plus. Okay, so if you total up the charge here, which is -2 and +2, you get 0 charged. Yeah, and then how many ammonia do we need to add on the left hand side? So if you just count, so that would be 4 and 1, and that would be 5. Okay, and then this will be the suggested equation, and the suggested color of the final solution would then be dark blue or deep blue, and then of course the identity of the complex giving rise to the dark blue solution will be tetraamine copper 2. Yep, so with that we have come to the end of our review, and I hope you find this useful, and do remember to visit the aqueous chemistry, the extra aqueous chemistry on cobalt 2, which was done up previously. Yeah, because I think it is highly relevant in order for you to have a deeper appreciation of this question, in our case here, question 2a.